I'm Tatsuya Iwano, PhD student from Kyushu University. Today, I'm going to talk about, as introduced, in situ 3D analysis for deformation-induced Martensitic transformation in metastable austenitic alloy by synchrotron X-ray. In metastable austenitic alloy, the phase transformation from FCC to BCC structure occurs when external deformation is applied. This is deformation-induced Martensitic transformation, so-called alpha prime Martensitic transformation. This alpha prime Martensitic transformation improves mechanical properties of austenitic alloy, such as strength ductility balance, fracture toughness, and fatigue property. Some mechanisms have been proposed to explain these improvements. However, these mechanical properties and alpha prime Martensitic transformation process across temporal and spatial scales have not yet been linked. So it is very important to investigate the alpha prime Martensitic transformation mechanism to understand their relationship. And some methods have been applied to observe the alpha prime Martensitic transformation process and morphology. For example, in situ EBSD analysis tracks the two-dimensional transformation process, and neutron diffraction detects crystallographic information at each deformation step. And 3D EBSD observe the 3D morphology and crystallographic information at the same time. But when it comes to the transformation process in temporal and spatial scales, in situ 3D analysis is very important to understand it. So the objective of this study is to visualize and investigate the alpha prime Martensitic transformation process by in situ 3D analysis. So in this research, we performed X-ray CT and XRD analysis by synchrotron X-ray to achieve the objective. X-ray CT can visualize the internal structure of the material and track the structure change non-destructively. On the other hand, XRD analysis can acquire the 3D crystallographic information. So by combining these two techniques, we tried to achieve in situ 3D tracking of alpha prime Martensitic transformation process. So the material used in this study was metastable austenitic alloy type 301. According to the results of EBSD analysis, this material contains only austenite phase at the initial state. We performed a tensile test on this material with crosshead speed 0.2 millimeter per minute and performed X-ray CT and XRD analysis at each deformation step. In this research, we obtained crystallographic information and 3D images of martensite products simultaneously. For XRD analysis, we scanned the specimen surface with X-ray pencil beam and rotated the specimen 180 degrees to obtain 3D crystallographic information. The combination of these XRD analysis and X-ray CT allowed us to characterize and index the crystal orientation of martensite products in 3D. So now let me introduce the results of X-ray CT. These are the reconstructed images at different camera distances. At 50 millimeter, we can distinguish between austenite and martensite phases, but their contrast was not clear. So as we increased the camera distance, the contrast between two phases became clearer and easier to identify both of two phases. But increasing camera distance also decreased the spatial resolution due to the refraction contrast. So we selected 150 millimeter as a camera distance for the best contrast and spatial resolution. So now let me move on to the results of in situ observation by X-ray CT. These are the reconstructed images at each deformation step. In these steps, alpha prime martensite product appeared as the dark gray values and indicating that alpha prime martensitic transformation progressed with increasing strain levels. In addition, no martensitic transformation was observed at non-deformed stage. So from 3D images extracted from these regions, we found the volume fraction of martensite product increased with higher strain levels. So in this way, we achieved non-destructive 3D in situ observation of alpha prime martensitic transformation by X-ray CT. To investigate the martensitic transformation behavior in more detail, we focused on the region of interest at the strains of 5.4 and 8.2%. The 3D images of martensite products showed that the martensitic transformation occurred along each specific habit planes. And each martensite product belongs to one of the 4 groups sharing the same habit planes. By XRD analysis, we also characterized the crystal orientation of each martensite product. First, we obtained these parameters to calculate the scattering vectors perpendicular to the scattering planes from these diffraction spots at each scanning position. And then we defined 2 kinds of crystal matrices, G0 and G, representing the initial and rotated state of the unit cell from 2 arbitrary scattering vectors. And finally, we determined a crystal orientation as a rotation matrix from G0 to G. And next, we indexed these crystal orientation candidates to each martensite product. After calculating the scattering vectors, we associated them with the position of martensite product obtained by X-ray CT in the specimen coordinate system X, Y, and Z. And then we determined the crystal orientation candidates from these associated scattering vectors and gathered them with misorientation less than 3 degrees. And finally, we indexed the most gathered crystal orientation candidate as a crystal orientation of each martensite product. Similarly, we associated the scattering vectors of austenite phase to each martensite product and calculated the crystal orientation of austenite phase around each martensite product. So by this XRD analysis, we determined the crystal orientation of both martensite phase and austenite phase around each martensite product. The crystal orientation relationship, known as phase orientation relationship, was analyzed. The difference of angles between close-packed planes and close-packed directions were less than 10 degrees, respectively. So as a result, we could index 1 variant out of 24 variant combinations to each martensite product, as shown here. So we also determined the habit planes of each martensite product by analyzing the crystal orientation of austenite phase. First, we calculated the normal vector against 111 planes in austenite phase. And then we derived the function of planes parallel to each martensite product by the least squares method and calculated the normal vector against the planes. And then finally, we calculated the difference of angles between these normal vectors and defined the Miller index with least difference of angles as the habit planes of each Martensite product. So as a result, the 4 groups of Martensite product, as mentioned before, had the habit planes along each 111 planes, which can be represented as 4 CP groups. By the way, previous research have reported that alpha prime Martensitic transformation tends to occur at the intersection of epsilon Martensite bands. So based on this, alpha prime Martensitic transformation is expected to related to the slip deformation in material. A Schmidt factor is an effective parameter to consider the slip deformation. So we calculated the Schmidt factors of 0, 1, 1 direction on 1, 1, 1 planes at each CP groups. Comparing the highest Schmidt factors at each CP groups and fraction of CP group given by this formula, we found the positive relationship between them. And this result indicated that alpha prime Martensitic transformation is dependent on the Schmidt factor of this slip system. So in summary, we performed X-ray CT and XRD analysis on alpha prime Martensitic transformation. In X-ray CT, we could visualize and identify the austenite and martensite phase and track the 3D transformation process non-destructively. By XRD analysis, we determined the habit planes of each martensite product, and the result indicated that alpha prime Martensitic transformation is dependent on the Schmidt factors of 0, 1, 1 direction on 1, 1, 1 planes in austenite phase. That's all for my presentation. Thank you for your kind attention.